Adam Johnson. Thanks very much for everyone coming out and see 5 slides. Kristen, this one here. I'm really pleased that everyone is here. I'm really pleased that John gave me the opportunity to extend my sabbatical talk. I'm a little disappointed that more of you weren't here for the original talk, but I'm delighted that you're all here now too. And I will, let's see, slideshow. This is something many of you who know about my sabbatical work recognize that I was on several side projects, and this simply was one of those that I didn't get to describe earlier. I'm trying to, am I backwards enough?
Yeah. Yes. I think it's on the timer.
It's on the what?
Maybe time, so it's going to.
Well played, Chris.
Are you stalling?
I'm trying to make sure it doesn't advance.
It's going to advance. Do we know how to turn off the timer?
I think you did.
Oh, we did. You did turn it off.
Yeah, I totally did. So one of the things that I was able to investigate during my sabbatical that I didn't get a chance to talk to you about earlier was states of matter. And states of matter, as you all understand, in physics is simply, well, it's interesting because we study matter and we study them in all kinds of states. Utah, Wyoming, other states as well that aren't Utah or Wyoming. Those states we study. I'll take questions at the end.
Is
I said I would take questions at the end. Dr. Hutchins, thank you for your contribution. So in this particular case, we're going to study those states with these things known as pumpkins. And you can see how pumpkins are an appropriate model for many other systems and objects in our universe. Ballistic weapons. We also have chemical changes as well as phase changes, physical changes, which you see up in the upper left here. And we have weapons of mass destruction. So all of these various states of matter and the modeling we can do with these objects known as pumpkins is the subject of this talk. I admit I am still myself trying to understand these kinds of ideas completely, and actually giving this talk is an opportunity for me to kind of explore the ideas. For example, we have these things called phase diagrams or phase graphs, or temperature versus pressure kinds of plots, and we do interesting things with them, such as put dots. And often between the dots we put these things known as curves, and in between curves we color them with colors that are complementary to pumpkin orange. We do that so that you can see the contrast in these graphs. No, I'm kidding, of course. This is showing the various phases or states of matter for our pumpkin. We have a liquid phase, solid phase, a gas phase, and then, not shown here, the exciting triple point of the pumpkin. The triple point is this. Well, that's above the level of this particular audience. So I'll say that's a good problem for the reader. Suffice to say, triple points involves trios, and they're anyway. So these various states. This is our liquid. This is something I don't recognize at all. I had a student actually prepared this slide. This is a solid phase. This is an interesting mixed phase. It's partially liquid, partially solid, glued together. But we use trigonometry to study this. You can see it's pi. It's also not beneath the level of this audience. Anyway. When we're studying all of these different phases, of course, we want to see how do they change from one phase to the next. Many people call this cooking. And it basically starts with this. You get something that's really hot, and you get something that's really cold, and you put the pumpkin in between those things. And depending on how hot the hot thing is and how cold the cold thing is, that determines what kinds of things you're going to produce from this pumpkin and what kinds of state that will end up in As we see here, we've got a graph. Again, I'm using them all the time since I've introduced them to you in the first slide. I thought I would use them again. The graph has temperature on it and it also has other things. That graph, we can show that there are different kind of costs and gains of these by varying these temperatures and these other things. If you get your temperature up really, really high, it can be done through a variety of ways. Broiling, for example, grilling, microwaving. We've got a little asterisk there for reasons that are, again, not really part of this talk, but it's really quite interesting. But I think that my favorite is probably the deep frying of the pumpkin, because that allows for, well, we talk about, well, it's deep, frankly. You get these kinds of nice kind of scaly fryer kinds of things on the outside, and then you spontaneously combust the stuff that's in the center. It's dangerous, but absolutely delicious. These kinds of steaks. That triple point I was talking about, it's in here. It's amazing that it would happen that way, but it's hidden deep within the nucleus of the pumpkin. So it's a nuclear physics issue. Strangely enough, we often talk about the solid state. We talk about, I was actually just doing this in class today, it's solids, liquids, gases. But then there's this fourth state. Incredibly interesting. Clearly, you can see right away it will be interesting because you've got fractions. Fractions, Greek letters. One of these is known as the permittivity of free space, which I was just explaining to some people over lunch. And then we have the wavelength of the pumpkin. Some of you are laughing like that would be ridiculous to have a wavelength of the pumpkin. If you can get the wavelength small enough, and this is where the fourth state of matter is really interesting, small enough wavelengths, you can actually get the pumpkin to quantum tunnel through walls while in the triple state. Absolutely unheard of. Some people light the pumpkin on fire just because they think it looks cute. And in fact, when raising that temperature to do the opposite of what I so the details aren't important. But if you can modify the temperature to such an extent, you can actually get the wavelength short enough that you can launch the pumpkin through walls and quantum tunnel into other people's boats. Finally, I hope. We sometimes think, well, if you have 3, there could be 4, but surely 4 would be enough. No. There could always be a fifth state of matter. The Bose-Einstein condensate, we're used to taking subatomic particles or just the guts of atoms, which is strangely disturbing for me when we talk about the guts of atoms or atom trapping. We take atoms and we shoot lasers at them from all directions. And we get them stuck there. We can do this with a pumpkin. It's really hard. But if you work at it, with some, effort, yes, will make that condensate do the thing. And you get these, as clearly explicated by those. And this graph is interesting because there are no points on it. We just have lines, curves, and color. And maybe that's exactly where we should end. I'll take questions.
Tyler, you have time for a question? One question from Dan.
I know you were addressing the issue of states of matter, but I couldn't help but notice that the word center was spelled with the British spelling. Are you implying that Great Britain is a state?
It is a sovereign nation, and by definition in international laws, I'll explain later, it's a state, different than Wyoming in lots of ways.